if we envision a translation and we imagine, in this case, one triangle sliding onto another triangle, mapping onto it, as we've discussed before, one way that we can envision that or describe that is using something called a vector. So a vector is basically, it's kind of like a ray that we've talked about in geometry before, but it's something that has both direction and something called magnitude, which in this two-dimensional space is basically the length of that, what's ultimately going to kind of look like a line segment. So for example, if I draw starting from point A, if I connect point A to its corresponding point, which is A prime, this would be the vector that's representing the movement for this translation, for this rigid motion, to get from A to A prime. So we can see that this vector has a direction. It's showing us the direction of the translation. It also has a magnitude. So the magnitude of this vector is the length from A to A prime, from its starting point to its ending point. And we already know from other moments in geometry where we found the length of a segment that I can just do Pythagorean theorem to think about that. And so really in the two-dimensional space, this vector is just a combination of the vertical and horizontal movement, which I could think of as their own vectors. But to simplify things here, we're just going to kind of follow what we're already used to when it comes to using Pythagorean theorem. So I can see I have a length of 3 here, and 1, 2, 3, 4, 5, 6, 7, 8. So in order to determine the magnitude of this vector, I can do 3 squared plus 8 squared equals c squared. So 9 plus 64 equals c squared. So that means radical 73 is the magnitude of this vector. So because we're doing a rigid motion here, so every single vertex is being transformed in the exact same way, that means the vectors connecting C to C prime and B to B prime are also going to have the same direction and magnitude because the entire triangle is being translated according to that same vector.